Hello everyone, and welcome to this video where I'll be taking you through a sample question on the objective: determine the derivative of a parametrically defined curve with trigonometric functions. So here I am at Knewton.com in their Knewton Alta program. I'm in the instructor mode, so you can see questions with answers. It's going to be a little different when you're taking it if you're taking it as a student. But I just want to go through one question related to this particular objective. And if you can follow along with this one, hopefully it'll make working on other problems in this same objective that much easier. And as always, I would suggest, if you're somewhat familiar with the topic and the material, pause the video, try to work out the question yourself first, and then come back, watch me do it, and compare your work to mine, see how well you're grasping things. All right, so here we are. Now again, I'm in this instructor mode here. You can see the answer down here already to the question I'm about to read. But I'll show you how we get there, all right, on paper. So here we're asked to determine the derivative of the parametrically defined curve represented by the equations x of t equals -4 times the cosine of 5t and y of t equals -6 times the sine of 5t, where t is considered, the parameter that the x and y coordinate of our location, depends upon. And as you change the values of t, these two equations would trace out a curve on the xy plane, and we're asked to find the slope, some expression to represent the slope of the tangent lines to that curve at any moment. So that's that dy over dx. All right. So one way to go about it would be to try to eliminate the parameter, right? Write an equation for the curve in rectangular form with just x and y and no t. So you may recall with the trig functions here, like sine, they have sine of 5t, cosine of 5t. I would, solve for isolate the sine and cosine, square both sides, add them up, and it should be equal to 1. I'd get x squared over 16 plus y squared over 36 equals 1. The equation of some ellipse. And I'll go to Desmos in a little bit, desmos.com, and show you that these two equations, trace out an ellipse. And then you can find, dy over dx or y prime of x, the slope of the tangent line to any point on the curve, implicitly from there, or explicitly if you solve for y, get y in terms of x, whatever. I'd say that was the longer way of doing things, though. So what they want here is just a quick short one, right? Just a short way of doing things. Get the slope of the tangent line to some parametrically defined curve in terms of the parameter. So you notice how t is still in the answer here. So you can find the slope of the tangent line to any point in the curve. You just have to know what the value of the parameter is there. But finding this is pretty simple, and I'll show you. All right, so on paper, here are the parametric equations we were given, right? X of t is, -4 times the cosine of 5t, and y of t is -6 times the sine of 5t. All right, and when we're going to find, dy over dx, right? The y prime with respect to x, the slope of the tangent line to the curve being traced out. When you're in parametric form still, you can involve the parameter here by, and I put this in quotes because technically you're not dividing by dt, but if I divide, the numerator and denominator by dt, we get something equivalent to the original. I did develop this, why this is, in a previous video, so I'm not going to go through that again here. If you haven't watched it, that's okay. Just remember this. This will be helpful. So the derivative of y with respect to x, right, slopes of tangent lines to this curve, will be equivalent to the change in y with respect to t instantaneously divided by, and then, the change in x with respect to t at an instant, right? Or the, x, you could call this y prime of t, y prime in terms of t divided by, and then x prime in terms of t. And this is how we're going about finding slopes of tangent lines, derivatives to curves defined parametrically. And each of these are pretty easily found from our parametric equations. I'm going to assume that you remember basic derivatives of trigonometric functions from your previous Calc 1 experience. All right, so going through the parametric equations again, x of t is this, so x prime, or you could call it dx over dt, same thing, would be -4, right? The constant multiple stays. And then you might recall, right, the derivative of the cosine of something was negative sine of that thing, right? So times negative sine of 5t, but then we got the chain rule going on. I'll put that in parentheses so it doesn't look like minus. And then times the derivative of the expression inside the cosine, right? There's clearly a composition here, and then, times 5. So when all that's simplified, -4 times -1 times 5, that's positive 20 times the sine of 5t. And that's going to go in the denominator of my first derivative expression. So 20 times the sine of 5t. Okay, and then we have y prime. Again, we could also call this, dy over dt, right? It's going to depend on this parameter t. It's -6 times, and then the derivative of the sine of something was the cosine of that thing multiplied by the derivative of the expression inside it. So chain rule, right, times 5. So we have, -30, you have -6 times 5, -30 times the cosine of 5t. And that's going to go in the numerator of the expression representing dy over dx here, the slope of our tangent lines, and -30 times the cosine of 5t. And this is great. This works. All right, this expression here is going to give us the slope of the tangent line to any point on the ellipse traced out. Remember I said this would be an ellipse. I'll show you in a second. This will give us the slope of the tangent line anywhere. You just have to know the value of t, though, at the point that wherever point you're at on the ellipse, you have to know the value of t that got you there in order to plug it into here and find the slope of the tangent line. Now, of course, we have to simplify things, right? So dy over dx, let's see, -30 over 20, those have a common factor of 10, so that'll be -3/2 times, and then the cosine of 5t divided by the sine of 5t. A quicker way of writing that would be the cotangent. Remember cosine over sine? Cotangent of 5t, right? And this, I'll put a different color around this one. This is what they're showing me in my answer here in the instructor mode, right? Going back to the website. The -3 cotangent of 5t all divided by 2, which is the same thing as what I wrote with the -3 halves times the cotangent of 5t, right? Okay, and again, just wanted to show you the ellipse, right? Just here at Desmos.com, free online graphing calculator. I'm going to go enter these parametric equations. Now, when you enter parametric equations, you have to enter as an ordered pair. So left parentheses, the x coordinate in terms of t was -4 times the cosine of 5t. The y coordinate, so then comma, the y coordinate -6 times the sine of 5t. And right now they got the range of t from 0 to 1. Just gonna go all the way around here, 0 to 2 pi. We're in radian mode, by the way. You can go to settings and see that you're in radians or degrees. You should be in radians in calculus, right? There, clearly an ellipse. And the expression we just got with the -3 halves times the cotangent of 5t, should give me the slope of the tangent line to this curve at any moment, as long as you know the value of t. Okay, wonderful. All right, so again, hopefully watching me do this one here will help you out with other similar problems in this same objective. And thank you very much for watching.